we're going to approximate the area underneath the curve y equal x squared, and we're going to do this by drawing rectangles. Like in this case here we have 4 rectangles which approximate the area under y equal x squared from x equals 0 to x equals 2. Now we're going to find a formula for the sum of the areas of these rectangles. Each rectangle is going to have the same base. In other words, here the base is 0.5 or 1/2. So they'll have, so we're just going to take the interval from 0 to 2, and we're going to, in this case, we divided it into 4 intervals. And in general, we'll have a formula where we divide the interval from 0 to 2 into n intervals, and we'll have a formula for the sum of the rectangles that are above those n intervals. Each rectangle hits the curve on the right hand side. Okay, you see here's the rectangle, the right side of the rectangle, that's where it's going to hit the curve. This formula, this sum formula, is going to involve a known formula, the formula for the sum of squares of numbers. In other words, the formula for the sum of 1 squared plus 2 squared plus 3 squared plus 4 squared, etc. So first we're going to look at that formula. Here's the formula that we need, formula B, and you'll prove that formula. We're going to prove formula A, this one over here. Wait, let me just pull this down 1 second. Okay, there we go. We're going to prove formula A, and we'll prove it by a method called induction. All right, so let's just talk about induction. If we have a formula that involves n, where n is an integer, and if the formula is true for all the values of n, let's say from 1 and up, then it's appropriate, or sometimes it can be proven using this method called induction. And here's what induction involves. You want to prove the formula, or show it's true, show the formula is true for n equal 1, or for n equal whatever the starting value is. In this case, this formula starts off at n equal 1. So we want to show it's true for n equal 1, and that's going to be very easy. And then we're going to assume that it's true for n minus 1. And using this assumption, using this one over here, if we show it's true for if we assume it's true for n minus 1, we want to then show, using this assumption, that it's true for n. And if we do that, then the formula will be proven by the method of induction. Now let's think about why this works, and I'll give just an analogous situation. Let's suppose that you want somebody to build a brick wall for you. Okay, now let's assume that the person can build the first layer. All right, so the person can put down whatever the foundation is for the brick wall. Okay, and they can build the first layer. That's the n equal 1 situation. All right, so suppose you know that that's true. Okay, and let's suppose you also know, you assume true for n minus 1. In other words, you know the person can build, you know that if there is a layer, the assuming true for n minus 1 is analogous to if let's say there might be layers in between, if the n minus first layer is there. This is what this assumption means. If the n minus first layer is there, then we're going to show that the person can build the next layer on top. So this is what we assume. We assume that if an n minus first layer is there, then we're going to prove that this brick layer can put a layer of bricks on top. So anytime there's a layer below, they can add a layer above. That's what we have to prove. Well, if that's true, then don't you think that this person, this bricklayer, can build an entire wall? If they can build a first wall, and any time there's a top layer or an n minus first layer, they can build on top of it. So don't you think it means that they can build the entire wall? Because after all, they could have started at the bottom and built the next one, the next one, the next one, and the next one, and gone all the way up. So that's what we do with induction. We show that the process can be started. Show it's true for n equal 1. And if it's true for n minus 1, then it must be true for n. So in other words, if we can show this, then really we could have started at the beginning. That would be our n minus 1. All right. And we could have, since we can always go up one level, that's what this is showing, we can always go up one level, then we could have started at n minus 1, and we could have proven the formula for n equal 2, 3, 4, 5, all the way up to n. Okay, that's why induction works. All right, I hope that was clear. But anyway, let's do one proof. Let's prove this first formula, and I'll explain what this first formula means, but let's prove this first formula for using induction. This formula says that we can add the numbers 1, 2, all the way up to n, and we can do it using this little expression. Okay, in other words, for example, if we add 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, so in this case n is equal to 10. All right, then that should be equal to 10 times 10 plus 1 times 11 divided by 2, all right, which comes out to 55. All right, anyway, let's try it. Let's just start adding. All right, so what do we have? Here we have 3 and another 3 is 6, 10, 15, 21, 28, 36, 45, and 10 is 55. Okay, so it seems to work in this case. All right, and now the proof by induction. Okay, so here we go. So first, for n equal 1, well, that's easy. That would just be 1. Okay, now is 1 equal to 1 times 1 plus 1 over 2? Okay, yes it is. All right, so we're done with the n equal 1 case. Like I said, that's usually easy. And now let's assume that it's true for n minus 1. In other words, let's assume that the sum I equal 1 to n minus 1 of I, that would be 1 plus 2 all the way up to this time, instead of up to n minus 1. Let's assume that that's equal to, and now in this formula, wherever you see n, put n minus 1. So for that first n, we're putting the n minus 1 version. N minus 1 goes there. Here, n minus 1 plus 1, that comes out to just n, and divided by 2. Okay, put n minus 1 here, and we just get n. All right, so we're assuming that is true, and we want to show that the formula is true, that this formula now is holds. So now for n, okay, we have the sum I equal 1 to n. Well, that's equal to, first just add up 1 to n minus 1, okay, and then add the last one, which is n. So that's the same as adding the numbers 1 to n. You add up to n minus 1 and the last one. All right, so this is equal to, according to our assumption, we're assuming that this piece is equal to this. So we're using the assumption. So this is equal to n minus 1 times n over 2. And now we add in the plus n. And just get common denominator, and let's add these together. N minus 1, n over 2, plus common denominator, okay, 2n over 2. Okay, and so here we have, let's multiply through here, n squared minus n plus 2n over 2. All right, keep going like terms. So we have n squared plus n over 2. Now, this is the formula that we want to get right here. You see, n times n plus 1 over 2. And we do have that. Just factor out the n. And we do have that. Okay, so that proves the formula that when you sum the numbers from 1 to n, you can use this little shortcut formula, and that's what we have here. Over here we showed that for n equal 10 it does work, and now we prove that in fact it works in general. So what I'd like you to do is use this same method to prove the other formula, b, because b is what we actually need. This one, b is what we actually need for the x squared calculation. Here we have another formula, formula c, for the sum of cubes of numbers, the cubes from 1 up to n cubed, and I'd like you to prove that formula as well by induction. So now we want to find the area under y equal x squared from x equals 0 to x equal 2. Okay, so here's a picture. Here's a picture with 4 rectangles, and we're going to actually come up with the formula for the sum of the area of n rectangles. All right, let's look at a general function. Okay, so we're just going to look at some function f of x from a to b. All right. And we're going to divide this into n intervals. Let's say a is x0, b is xn, and let's say a general interval will be from, let's say, x I minus 1 to xi. All right. So, and the rectangle will hit the curve on the right hand side. So first let's talk about the length of the base. Well, the length of the base is going to be the entire length, which is b minus a, and since we have n of them, it's b minus a over n. Now the height, this point is going to be the height of this point, because that's where it hits the curve, and the height of this point is f of xi. So let's say this is a I, the ith rectangle. So, or the area of the ith rectangle. So AI is f of xi, the height, times the base. And if we have n of these rectangles, then the sum of the areas will approximate the area under the curve. So that will be the sum I equal 1 to n f of xi, and then we have b minus a over n. All right, so now let's talk about our example y equal x squared. So here's f of x equal x squared, and here our x0 is 2, and here's our xn. So if here's one rectangle, the ith rectangle, all right, so let's look at these 2 points. First of all, the length of the ith rectangle, this length over here, is 2 minus 0 over n, or 2 over n for each rectangle. Okay, so now let's look at the endpoints of the intervals themselves. So the first one is 0. The second one is 2 over n. We just keep on adding to 0, keep on adding 2 over n to get to the next one. So the next one's 2 over n. The next one is 2 over n times 2. In other words, 2 over n plus 2 over n, 2 over n times 2. And we keep on going like this. So for the ith endpoint is going to be 2 over n times I minus 1 on the left, and on the right, the endpoint is 2 over n times I. Okay, 2 over n times I. So if this is the ith rectangle, then the area is equal to f of xi times 2 minus 0 over n. Okay, so that's going to be, take this is our xi, and substitute it into x squared. So we have 2I over n squared. That's our f of xi times 2 over n. Okay, so now the sum of the areas, in other words, let's do it down here. The sum of all these areas, I equal 1 to n, for each rectangle, is the sum, I equal 1 to n. Let's square this out, and we have 4i squared over n squared times 2 over n. Now, it's important to realize that the n's are not changing in this sum. In the sum, I is the one that's changing. I is changing. It's going from 1 to n. So we can take 2 over n cubed and this 4 and put it out in front. So in front, we're going to have 4 times 2. We're going to have 8 over n cubed. So here we have 8 over n cubed. And here we have the sum of I squared, where I goes from 1 to n. So this is what we have to, this is what we're going to calculate. We're going to use our sum I squared formula and to figure this out. And so the area of n rectangles is going to be 8 over n cubed times this. So here's what we have so far. The area under y equal x squared from x equal 2 to x equal 4, from x equals 0 to x equal 2, from x equals 0 to x equal 2, is approximately equal to 8 over n cubed times this sum. And we have a formula for this sum. That was formula B. So we're going to replace this with the right-hand side of that formula. So this is equal to 8 over n cubed times, so we have 8 over n cubed times, and this comes straight from, I'm just going to copy over formula B right here, n times n plus 1, and that's one of the formulas that you're going to prove yourself using induction, 2n plus 1, and here we have 6. Okay. Of course we can simplify this. All right, just reduce that a little bit. All right, replace that with n squared, and here we'll divide by 2. All right, so we have 4 over 3, and here we have n plus 1 times 2n plus 1 over n squared. So if we have, for example, 100 rectangles, all right, then this would be equal to 4/3. 100 plus 1, that's 101. 2 times 100 plus 1, that's 201. Over 100 times 100. Okay. Over 10,000. Okay, so if we do the calculation, just figure this out, this is what we get, 2.7068. So this is the approximate area. Since we used a lot of rectangles, 100 rectangles, it's a pretty good approximation. All right, now let's get a exact value by going back to the sum of n rectangles, the sum of the areas of n rectangles, and take the limit as n goes to infinity, and that will give us an exact value. So that's going to be our second method for calculating the sum. The first one was an approximation. The second is going to be an exact value. So let's do that over here. It shouldn't take too much space. All right, so let's look at the limit as n goes to infinity of the sum of I equal 1 to n of these areas. Okay, so in other words, the sum of the areas of n rectangles, and take the limit as n goes to infinity. Okay, so there we have, I'm just gonna almost copy this sum. I just want to multiply this out. So if we multiply this out, we have 2n squared, and then for the middle term we have 2n plus n, that's 3n, plus 1. Okay, we could just look for this, for a polynomial over a polynomial, we could just look at the highest order terms when we take the limit. So it's a limit as n goes to infinity. We still have the 4/3, and then we have 2n squared over n squared, and the n squares cancel, and so we get 8 over 3. All right, so 8 over 3 is 2.666, etc. So we got something, this approximation is close. This is 8 over 3 is the actual value, so it's pretty close. All right, and finally, so this was an approximate area. This is an exact area, 8 over 3, and without calculus. And now let's use the fundamental theorem and just simply integrate to get the exact value again, to get 8 over 3 again. All right, so here we go. Let's now area, our area is equal to the integral from 0 to 2 x squared dx. Okay, so power rule and 0, 2. So we quickly get 8 over 3. So there we have 3 ways of finding the area underneath the curve x squared from 0 to 2. One is approximate, and the second two are exact. So now I'd like you to do the same thing for some other functions. All right, so here we have the instructions. So now I'd like you to do the same thing, do the same 3 methods for finding the area under first y equal x cubed, and then under y equal 2x plus 1, both from 0 to 2. So for y equal x cubed, you'll need the sum of I cubed formula, and for y equal 2x plus 1, you'll need the sum I formula. All right. Now you could also, if you're into computer programming, you can write a computer program for the second part, for the first part, for the approximation, when you are summing n rectangles, and you could first try it for n equal 1, 2, etc., and print out the various values and see how quickly or how many rectangles you need to get close to the actual area. All right, so this, together with the proof of the 2 induction formulas, that is formulas B and C. All right, so that'll be that. That's your honors project. And if you want, you could continue on and do more and look at numerical methods of integration as well, which is I think that's section 5.6. This material comes from section 5.2. And if you have questions, I'm always available, in my office after class, and also earlier in the morning, so you can talk to me in my office as well.